what I'm going to go over today for class is something that uses, well, we're going to finish our notes with solving cubics. So we started yesterday, Thursday, by using this principle that we have this way of testing if a possible factor is in fact a factor, is actually a factor, by finding the root of each of these values, or any factor you can imagine, plugging it in, and seeing if it gives you 0 when you do that, plugging it in for x. And if it gives you 0, then that possible factor, it actually was a factor. That's what's called the factor theorem. Okay, so with that tool alone, we can actually factor some pretty sophisticated stuff, and that's actually what we did here with this last page. We took a sophisticated polynomial, we found a root, and then we used long division. We found a factor, used long division to divide the polynomial, and then factored the rest. Now, that's fine, but sometimes, I should say, there's a maybe more sophisticated idea that we need to talk about. That's example 3. So we're going to stop and take a step back and look at an example here of a classic question type. And then we're going to get to this big fella here, the rational roots theorem. So yesterday we were sort of shooting in the dark, like, should we try to guess x plus 1? Is x plus 1 a factor? Oh, well, what about x minus 1? Or maybe we should try x plus 2, or who knows? And people were, I think, guessing pretty randomly, reasonably, because that's all we had to go on. So the rational roots theorem is going to supply us with a way to know exactly which possible factors to even try in the first place. It helps us to remove a lot of the other potential candidates. So we'll get there in a second, but that's the shape of the day. The shape of the day is first to talk about a nuanced, sort of tricky example that can pop up in factoring polynomials, using the factor theorem. Consequence of the factor theorem, really. And then we're going to get into this big rational roots theorem, which is just a tool we can use so that we don't have to guess and check as many different potential factors. It can reduce our choices to a few. All right. So let's start with this one. All right, so question 3 says, what values of b, for what values of b, which is b, would x plus 1 be a factor of this? Okay, so to answer this question, we need to understand the factor theorem and what it says. All right, so the factor theorem says if x plus 1 is a factor, then if we allow this function to be p of x, then p of negative 1, I plug in negative 1 for x and for all these inputs, it should equal 0. And that's what the factor theorem allows us to conclude. It's an if and only if statement. So it's also if this value is 0, then this is a factor. So we can actually conclude either way. Okay, so I said negative 1 because the root is equal to negative 1. All right, so that's what we're going to test. So is p of negative 1 equal to 0? So we'll test that. What we're going to do is we're going to say, well, we're going to find what p of negative 1 is, which means we're going to plug in negative 1 for all our values of x, plus b times negative 1 plus 6. And we're going to see if what value of b makes the whole left-hand side equal 0. Because as you notice now, we have a single variable in our entire equation, and it's b. And if we have just one variable, we can isolate that variable. And so we're just going to do some pretty simple algebra to get started here. Negative 3 cubed is negative 3, times 3 is negative 3. Negative 4 times negative 1 squared is 1, so negative 4 times 1 is negative 4. And I'm going to rewrite that as negative b, it's like negative 1 times b, plus 6, and that's all equal to 0. I'm going to simplify all this before I do anything else, so I've got negative 3, take away 4 is negative 7, plus 6, that gives us negative 1 minus b equal to 0. So I could move the 1 away, which is usually what we want to do. We want to get everything away from b's side. But b is negative here, so actually I'm going to add b to both sides. And that tells me that negative 1 is equal to b. In other words, if b equals negative 1, x plus 1 is a factor of p of x. And that is a question type that shows up every now and then. And what it does is really test that you really understand what the factor theorem really implies in the first place. Okay. Now, that's fine. That's a little aside. And we're going to get you some practice with questions like that every now and then. And there will be question 3, which you can practice that helps you tackle a question like this. All right, now, the rational roots theorem. This is a theorem that, in theory, you can get away without knowing, practically speaking, unless somebody asks you to list all the possible rational roots of some polynomial. But if you're just trying to factor it, in theory, if you have infinite time, you could try infinite rational roots and or try infinite different factors for a polynomial and see which one works by finding which one equals 0 when you plug in the root. However, we got to see yesterday in a way that I actually thought was pretty good, even though it wasn't intentional, that we ran into frustration by trying to factor things without using the rational roots theorem to help narrow our scope. Okay, so let's read the rational roots theorem. It's written in big math language in a really condensed way, which is great, because if you guys are going on to calculus, you're going to get used to reading statements like this and making sense of them. All right. So the rational roots theorem says the only possible rational roots, let's stop there. Rational means can be written as a ratio, like 3 over 2, or 4 over 1, negative 4 over 1, say. So those are rational numbers. Okay, and the roots that are you can write as a ratio, or otherwise get as a fraction, for any, this is a polynomial, it's a general form of a polynomial, are the form m over n, where m corresponds to our constant term, the last term. So that's our m, and n, the denominator, corresponds to the leading coefficient, a of n, leading coefficient. Rather, where actually, I have never seen this notation before, I'll be honest, but that's not exactly what the rational root theorem says, the way I phrase it, so I'll have to apologize. It's actually going to be m could be any factor of a naught, is any factor of the leading, no, of the constant term. And n, the numerator, can be any factor of the leading coefficient. All right, and let's do it in yellow. And n is any factor of the leading coefficient. All right. So we're going to use this process to reduce the number of roots we could possibly check. And I think this is going to make more sense when we put it into practice. So to find all the possible rational roots, we need to find all of the factors of the leading coefficient. So possible factors. So what numbers are factors of 2? Well, there's not a lot of them, right? There's 1, -1, 2, and -2. Or ±1, ±2. Okay, what about -9? The possible factors of -9 are, again, 1 can go into 9, -9. So can -1. 3, -3. Oops. Well, -9 as well. -3 is what I meant to write, and +9. Or ±1, ±3, ±9. Okay. And so the only possible roots for this polynomial, meaning x-intercepts, are the, what does it say here, m over n, where m is any factor of the constant term, the last term. So these are our m's, divided by any possible factor of the leading coefficient. So these are our n terms. So if we're looking at m over n, we're looking at any of these guys over any of these guys. So I'm going to start with 1 over +1. Okay, so that's just the value 1. -1 over +1. Oh, that's -1. So actually I could say plus or -1. Those are two possible roots. Also, I could do 3 over 1, or 3, and 3 over -1. That's -3. And I could do -9 over 1, which is -9, or 9 over 1, which is +9. Or it could be possible that the roots are 1 over 2, or its negative version, 1 over -2, or pardon me, 3 over 2 as negative version, or 9 over 2 and its negative version. And these are all of the possible roots of this polynomial. And so we're going to test to see which one makes them equal 0. So I'm going to test 1. And of course, this means we're looking for the factor x minus 1. So we'll check p of 1 here. So that'll give us 2, I'm actually going to abbreviate this, 2 times 1 cubed is just 2, minus 1 squared, minus 18 times 1, oh, I should say plus 1 squared, oops, minus 9, and does that equal 0? 2, 3, minus 18, minus, no, it's not going to equal 0. It's not equal to 0. Therefore, x minus 1 is not a factor. Okay. Now, how about, I'll try -1. -1, or x plus 1, the factor that corresponds with that root. So I'll try p of -1, and that says that I get 2 -1 cubed plus 1 plus 18 minus 9. Huh. Okay, and if I check here to -2 plus 1, it's -1. Okay, when I add 18 and take away 9, that doesn't get me to 0 either, so it's not 0. So therefore, x plus 1 is not a factor. Okay, now I can skip to 3. I'm not going to try x plus 1 and x plus 2, because I know that those aren't possible roots. So I'm going to skip straight to 3. Let's P of 3. All right, now is where I might need to do some calculator work. 3 cubed plus 3 squared minus 18 times 3 is 54 minus 9, and we'll just see what that equals. So we're getting into the right neighborhood here, I think. 2 27s. Oh, this is going to look good because that's 54. That's 9. That's negative 54, and that's negative 9. And that is equal to 0. So therefore, x minus 3 is a factor. And I might put a little box around that one because that's a big idea. Now, you might have guessed and checked other possible roots. Oops, that should have been a 2. Pardon me. All right. Let's talk about how to take one of these roots and test them. So we could have tested, say, negative, or let's just say positive. I have to keep our lives easy. All right, so then I would be testing p of a half. Now, if the root is 1/2, what's the factor? The factor is 2x take away 1. He said factor. It's a potential factor. We don't know if it is yet. So we're just going to test here. 2 times 1/2 cubed. So that's, all right, that's going to be a weird thing. And 1/2 squared is a quarter. Minus, this isn't going to work out well, minus 18 times a half, which is minus 9. Minus 9. All right, and I can see that this is not going to work either, so it's not equal to 0. So therefore, 2x minus 1 is not a factor. And that's how, when we use the rational roots theorem to list all the possible roots, when we have a fraction, we got to remember that that's going to correspond to a potential factor that looks something like this. Oh, and I realize now I've been doing C all along. So we're finding roots, and then we need to determine if they're factors or not. Now, I think it's very important to do those in the same step. Never find a root without making a conclusion about a factor, because that's actually, or potential factor, because that's actually what we're really doing here. So actually, that's what we're doing here. We're finding the factors, and we found x minus 3 is a factor. All right. So with that skill, that allows us to try all of these questions. And I'm going to assign these for homework for Monday. All right, so for questions like 4A, B, and C, you can test by plugging these into Desmos and taking a look at whether the x-intercepts you find make the graph that Desmos will plot for you. I'm going to try and... am I going to have time to make a video for that by Monday? No, I'm not, realistically. But email me if you have any questions. All right, good luck, guys.